Welcome, this is lecture number 59. In this lecture, we are going to talk about challenges and opportunity in digitally controlled high frequency switch mode power converter. So, in this lecture, we will first talk about stability aspect in digital control, particularly the effect due to quantization and sampling. Again, this lecture is just a brief introduction of digital control. We are just highlighting some key issue, but the digital control can be a separate course, because here we are just showing at the end that whatever we have learned in the previous lecture, if we can want to do in digital control, then what type of architectures are available, what may be their impact in stability, and what are the opportunity that we can move forward. But in actual digital control have many more things. Then we can say modeling and analysis of digitally controlled DC-DC converters, and then opportunity using variable frequency digital control architecture. So, first we will recall our fixed frequency high frequency voltage mode control DPWM, and DPWM here stands for digital pulse width modulator architecture, and this you have learned. That means your output voltage is sampled in digital, then it is compared with reference and generating the error voltage, then you have a compensator, and then the controller output is compared with a sawtooth waveform. The sawtooth is also generated inside the digital controller, and the comparator is a digital comparator. So, that means it does not require much of power, it is very simple. And then the whole there will be a dead time and half bridge gate drive. The dead time can be generated from here, and then we can actually control the switch. So, here the benefit we have discussed, that is a reconfigurable, this can control, we can do real time energy optimization, we can implement this whole block up to this switch, including the switch. The whole block can be inside one IC, right. So, this block, and we can do very fast prototyping, because the HDL code we can plug in into FPGA, do prototyping, and that Verilog code we can use to synthesize our actual ASIC. Then the digital control also provide the power management bus interface for interaction between multiple converter, because most of the system portable device that we will use that have multiple converters. So, there should be interaction among them or communication. We have also just shown in the lecture number 57 the effect due to quantization in digital control. That means, if we actually consider the sense voltage here, and then we have an A to D converter, right, and this is our voltage loop sense discretized or the digitized voltage. It is compared to the reference voltage and the compensator and a DPWM. Now, if there will be a clock, right, because we can initially assume, or basically the very simple, because for the time being here we are assuming there is a counter, it is just incrementing, and that is basically your kind of a digital pulse width modulator. And this increment size depends on the clock, T clock, at which clock you are using the time period of the clock, and which is used to increment this counter. So, T clock by T switching period is my duty ratio resolution, because this will set the minimum resolution of the duty ratio that can be achieved. And if you take a smaller and smaller clock time period for a given switching period, then you can reduce the duty ratio resolution, because this duty ratio resolution plays a significant role in the stability of the digital control, in the particular the quantization effect. If the resolution of the duty ratio is poor than, that means DPWM resolution, delta D, the ADC, because ADC will also have a resolution, right. Then what will happen? The quantized voltage, this may not be mapped all the time here and here, it may be mapped in between, and if so mapped in between, then actually you cannot get the perfect duty ratio. As a result, the duty ratio will back and forth between its upper and lower limit, and that may lead to limit cycle oscillation. So, exact duty ratio may not be achievable. So, you may not be able to lock the error voltage inside the zero error bin. What is zero error bin? Suppose if this corresponds to your actual output voltage, this control voltage, that means this voltage, if it is not mapped to particular number, then the error voltage here, so error quantized error voltage will not be 0 at steady state, because we want the quantized error voltage to be 0 at steady state, so that it will particularly become a number, then it is a constant number. So, if this is coarser, that means DPWM resolution poor than ADC, then you will end up with limit cycle oscillation, and this has been well reported, and these two are very highly cited paper. So, initially it was shown the steady state effect, that means the resolution effect, and then subsequently this paper shows the dynamic impact is also very important. So, if we take into account this quantization aspect, then this may not look like a limit cycle, it is like more nonlinear phenomena, but a limit cycle means there is a slow scale oscillation like this on top of the actual switching converter frequency. That means this is your converter switching frequency can be much faster, and you have a slow scale oscillation, and that we typically consider limit cycle oscillation. But generally switching converter in the fastest sense, it also is a limit cycle, but that means we have learned in the phase plane geometry, that means switching converter itself has a limit cycle because on off operation, but this limit cycle corresponding to each of this profile, they are very high frequency. But here we are talking about another limit cycle which is very slow. So, it may look like in the phase plane, it may look like something like this. That means due to limit cycle you will have this kind of oscillation, and on top of that you are getting this limit cycle oscillation, it will look like this. So, this kind of behavior you can find. So, it will actually chatter around this behavior. So, it will create lobe around this and it will move on with this. Okay. So, it will something like a torus. But actual we have just talked about the effect due to quantization. That means you have to make sure that the resolution of the duty ratio, this duty ratio where we are getting delta D here, must be finer than the resolution of the ADC. But this is not sufficient, because we have discussed in the previous class there is a sampling delay, right, and that delay is quite significant. And what was not investigated earlier, that what could this delay make, I mean along with this can it do. So, this is one of the scenario where you can see this is a different input voltage of the buck converter at 6 volts. So, here the output is 3.3 volt. This is my output voltage, my output voltage is 3.3 volt. Now, if you operate at 6 volt, this is a voltage mode control. You see during this particular time your duty ratio, actually your error voltage as if get locked to the 0 error bin and it stays, and you can see from the output voltage profile it stays, and in this time the error voltage, quantized error voltage becomes 0. So, output of the controller look like a fixed number, and that will lead to some natural or the open loop behavior of the converter, and due to which slowly it is increasing and it can hit the upper limit. Once it hit the upper limit, it again goes out of this band, and by that way it may not or never settle into this. But this is even with satisfying all these DPWM quantization criteria. Now, if you increase the input voltage, you will get at some point is a perfect stable behavior. That means it is periodically repeating, there is no limit cycle, nothing. Now, if you further increase, you may end up with somewhere where it is something similar to limit cycle, but not exactly limit cycle. So, it is a nonlinear complex phenomena, though it can be sometime there is a slow scale, I will not say oscillation, but periodicity, but this kind of behavior sometimes called coexisting attractor. But if you further increase the input voltage, then you may land up with situation where your duty ratio can saturate and it will lead to very large ripple in the current and voltage. And this may not be the only cause due to the quantization, because as if here the quantization criteria is satisfied. So, what was the issue? Here it was due to the sampling. And why it is so? Now, consider, so that we will discuss, because we have in this paper we have discussed that the cause of sampling can be, it can severely impact the stability of the system, whereas the quantization is a kind of a steady state behavior and that will cause some slow scale oscillation, but the sampling can lead to drastically different nonlinear phenomena, and in most of the cases it leads to deuterated saturation, where your RMS current everything increases drastically. Now, before we go into see what is the reason, if we take current mode control, the same scenario can happen. How? Suppose here I am showing a peak current mode control, mixed signal peak current mode control. We are talking about a mixed signal peak current mode control. That means mixed signal peak current mode control, in which the outer loop voltage loop is in digital and that is sample once per cycle, but the current loop is in analog, and that we have already discussed in the previous class. Here we are first operating at a lower proportional gain. So, it is we are using a PI digital PI controller, you can say digital digital PI controller, where Ki is fixed and Ki will have hardly any impact on such kind of stability, but we are changing Kp, we are increasing Kp. For lower value of Kp, you can see this is our switching clock, this is our FSW clock, and this is our duty ratio, or I will say gate signal, this is our gate signal. So, this is our gate signal. Okay. So, you can see it is repeating at every side rising of the clock, the current is repeating, it is a perfectly stable behavior. But if you go for next, this is again our switching clock, but they are not repeating. That means there is something instability, and we can see this subharmonic instability in current mode control often. But this is with very low duty ratio operation. You can see the duty ratio is much lower than 50%, much lower than 50%. This is when we change, we increase the Kp, that means we have increased the Kp. But here in every cycle you see there is an on off operation, that means on off operation is happening, but along with that there is instability. But if we further increase, again this is the switching clock, you will see, if you see this cycle, the switch is totally off, that means the switch is totally like off, there is no on. It may so happen if you go further up, the switch can be completely on. So, here it is unstable, the current loop is not stable, but along with that it has deuterated saturation, and that first one is called period 1 behavior, and this diagram is called bifurcation diagram. Again I am not discussing detail about this, this is called bifurcation diagram, and this is my sample current. That means, if I under steady state, if I sample the current at every rising, like I am taking this sample, and if I display in this axis for a given particular proportional gain, then I will get 1 point here, right, 1 point here. That means all inductor current will overlap, like they will keep on repeating the same place because they like a straight line, right. But if we increase, you will see this region you have some sort of instability, and that is exactly is happening. I am just showing qualitative plot, but it is not quantitative, it is not a exact point to point map. But here if you go to this region, there is a deuterated saturation, and this is called non-smooth bifurcation and it is called smooth bifurcation. Again this bifurcation terminology I am just using just to those who are familiar can look into this, but otherwise you can imagine that this is a kind of instability, where in this instability there is no deuterated saturation, but here there is a deuterated saturation. So, here we found that this is even for duty ratio much lower than 50%, and this high gain instability when we increase the gain, because we generally need a little bit higher gain because we want to go for optimal tuning, like large signal tuning, or we want to go for faster bandwidth, right, high bandwidth. So, we need some higher gain, and in digital control this may lead to such this kind of instability, and that was not explored earlier. So, what we found that this kind of stability does happen and it leads to high gain instability with due to saturation, and this stability analysis and design tool we have developed. What is the cause? If we take the voltage mode control, this is our sampling point, right. So, that means if I take this point and next sampling point is here. So, if we take about a periodic operation between two subsequent sampling, what can we expect? During the first sample the switch should remain off, and during the next sample also switch should remain on, in between the switch should be on. That means in the sampling instant the switch should be off, that is our desired requirement or the desired or expected waveform, and in between switch will be on, because when the switching clock will come the switch will turn on here, like switch will turn on here, and depending upon the duty ratio it can be smaller duration or longer duration, but the two subsequent sampling point here we are expecting they should appear in the off time, and in between they should be on. That means we should get something like a off, then on, then off. This is my state to off state, and this is my on state. So, off, on, off, but actually there can be many. If you take, so this is I will say my desired region 1, but here if you take between two sampling point, it can be off and fully on, it can be totally off, it can be on off, it can be totally on, it can be on off, and in between also there can be switching. So, there are such total 9 possibility can exist. So, if you take about analog control between two switching edges, that means a switch will on or off, right. This is one possibility, or it can be totally on or it can be totally off. In case of analog, because we take the sampling, it is a stroboscopic sampling, virtual sampling, there is no sampling in analog. So, if you take between two clock edges, because we are talking about this clock edges, so that in between two clock edges 3 possibility can happen, but here in between 3 sampling edges you can have 9 possibility, and this is the reason for such kind of instability. And if you do not take this delay properly, you may end up with chaotic behavior, deuterated saturation, such thing, and it was reported here. And subsequently we have also reported in last epic about this in current mode control. So, the reason is that how to justify, if we do sample data model, that means we can use this like a window at every clock edge. Here in our, for analog control we can use this window in synchronism with the switching clock, and we want to see the value when this intersect with this, it intersect with this, I would say surface, right, very interesting, and we want to map this value, the voltage and current, right, map, and we want to say in the state space, if we take current versus voltage in the discrete plane like In and Vn, so it will move 1 1 1. So, that means if you perturb and if they comes in the same line, then that means they are repeating in every cycle, then it will eventually become like a point. That means there will be no more movement of this point, or there is no, that means all perturbation have died out and it converges to a point, and there is a stable condition. Okay, so this, in order to get this kind of mapping of this point, you need to start with some initial condition here, then you obtain at the beginning, then use the solution, that means we will get the on state trajectory solution, then you get the off state trajectory solution, and we know about this, we have discussed very briefly at the beginning at the modeling technique. There is something called discrete time model, where we can get the solution of the state space equation and for individual subsystem. And if you get the total solution xn, then you can represent this xn in terms of xn minus 1, and that will create a map, and that is exactly what I am showing. But this is a somewhat I would say complex map, and it mathematically somewhat complex, but it is necessary to capture this kind of behavior. But this model can also be extended to get the perturbed discrete time model and to design the digital controller. So, the modeling technique in digital control, we can use a traditional small signal model which we have discussed throughout this course, and then we can approximate the delay due to the ADC, like a delay in the loop, right, that people also use, and then you can design a controller. But this will give somewhat approximate design very nicely, but this model cannot capture the kind of instability that may due to issue saturation, those things it cannot capture. So, that will be, in that sense this model is not accurate. The discrete equivalent of small signal model, that means it is totally in continuous domain, where the controller is designed in the continuous domain and then it map back to the digital domain by means of a transformation, that means either bilinear transformation or backward transformation and so on. Or you can get the discrete equivalent of the analog and then design the digital controller directly. But these two techniques are no longer, is not used so much because they cannot capture the kind of stability that happen in digital control. So, they are simple, but still some data sheets still use the application note, but discrete time model, large signal and small signal model particularly, is that now it is a very like a essential tool for designing digital control, which can predict this kind of stability, and also it can, from there you can get the frequency response and various other stuff. So, we can derive various transfer function for this, and this large signal model is very much needed in order to capture the kind of nonlinear behavior for different type of possibility that we have discussed between two subsequent sampling points. So, this I am not going to discuss this because, as I said, this is just a I am touch upon this technique, because we know about this traditional model, we can get this equivalent discrete time model little bit but all these require thorough lecture series to understand in detail. So, I am just touching this topic so that one can go through literature or resources and get some information. Now, stability of the mixed signal current mode control. So, we talked about stability of fixed frequency current mode control, and we saw at Kp equal to 7, there also it was Kp equal to 7, sorry, here you are using uniform sampling. That means, if we use a uniform sampling in variable frequency control, this is called multi-limit cycle oscillation, and that we should not use. So, here we are using event based sampling, that means we are sampling at the switching event, that means whenever the switch is about to turn on, then we are taking the sample and putting some delay so that we can capture the clean signal. So, here we are sampling with respect to an event, but here we are sampling with respect to time. So, that should be avoided. So, it is event based sampling is perfectly stable. And if we go to the highest gain, where we saw severe instability with due to issue saturation in analog in case of fixed frequency control, that means if we go back, we have discussed this, this is the case where it is Kp is around 12, and this is severe instability where due to issue saturation happen. But if you go to this technique, there is no due to issue saturation, and it can be shown that, in fact, it is shown in this epic paper that it does not lose the structural stability. That means, every cycle you will have an on off operation. So, it will never happen that fully cycle is on and off, because we are utilizing the minimum on time that we have discussed in constant off time control, and because of that your on operation is bound to come between two samples. So, if you take the sample in one off period, then in between suppose the on time is 0, but we are forcefully adding because this is the nature of this constant off time that we have discussed, and it is all commercial product they do have. So, because of we are introducing the on time just to make sure that there will be minimum on time, so then it will never have this structural instability. Now, you may ask me that on time may put a constant in the step down transient that we saw, but that can be anticipated in digital control, because during a large signal transient you can disable this minimum off time operation, so that the transient can be speed up, we can speed up the transient response. And in the last lecture we will show some of the result that we obtain. We can make the transient response extremely fast In fact, we can get the optimal response simply by using constant off time control by disabling this on time only during the large signal transient. But when it comes close to steady state, then we enable this and our whole kind of instability comes in steady state. So, we can avoid this structural instability under close to steady state, at the same time we get the fastest performance. And since in constant on time or off time control your current loop is inherently stable, so there is no stability problem. And we have applied this hysteresis mixed signal control. In fact, that was the event based sampling was first introduced here, and then where we have shown the stability in hysteresis control, all the stability criteria. And here the mixed signal current mode control, since we have used one sample per cycle, you can see for a wide range of input voltage variation, the current ripple band remains same. It is not affected, right? But of course, there is a switching frequency variation, because if you do not change the current ripple and if you change input voltage, naturally switching frequency will vary. Because in case of variable frequency operator, we saw for a given switching period the ripple will vary. Sorry, in fixed frequency control we saw for a given switching frequency the ripple will vary with the input voltage. Now for a given ripple, if the variation in input voltage happen, then the switching frequency is bound to to vary. So we can adjust it, because in digital, and here we have used only one D2A converter and one ADC and one analog comparator, and we are using a time multiplexing here. So we can get this perfectly stable behavior, and we can get the benefit of fully hysteresis, like a mixed signal hysteresis control, because the current is in analog loop. So it has analog current loop. So it has analog current loop. So we can get very fast transient response. We can get a ripple insensitive, that means the current ripple will be insensitive to system parameter, because it will be fixed for the whole cycle that I discussed. So you will get many features here and perfectly stable current loop, right? And you can tune the controller in order to get really fast transient response. Okay. So you can get event based sampling in variable frequency control, then parameter insensitive ripple band that we have discussed, but using only one sample per cycle. We can really get very fast transient response, and we can in fact configure either in peak, valley or average. So this can be a very effective technique for battery charging. We have seen other application where we need to precisely control the average current. So we can achieve very high current loop bandwidth with precise control of the average current. But only issue here, we need to sense the full current, and there are current sensor, lossless current sensing techniques are there, which can be used. You can, that means we know that inductor and resistance in parallel, we can put a resistance, so this kind of network we can use, and then by sensing this we can actually get the ripple information of the inductor without putting a physical resistance, and this is the DCR of the inductor, right. So this can be used. Again, the tuning method that we discussed for a boost converter, we have actually applied. That means if we apply this, because we have discussed already in the previous lecture in simulation how to implement this, and that can be easily implemented in digital, because the tuning parameters are in the digital domain in the voltage loop controller. So we can get extremely fast transient response, almost 8 to 10 times faster than the analog current controller, because that is limited due to the RHP0, because we have discussed that your crossover frequency we found for current mode control, it was RHP0 by 3. Even though you do digital control, we can adjust the crossover frequency when RHP0 varies, because that can vary due to the change in load current, change in duty ratio, then we can adjust in digitally controlled converter, but that is not enough. So we need to incorporate such large signal control to achieve really fast transient. So the digital control just do not, we should not go only for small signal where we can do some better, but since we are investing more because of ADC, DAC and other stuff, so we should take the best out of it. So we have compared that your peak current is pretty high, and if you put a current limit as well as the voltage limit here, so then we can get very good transient response, and it is much faster than, that means the linear control you need a 22 microsecond recovery time, with 320 millivolt voltage undershoot, whereas our large signal tuning takes 8 microsecond and 300 millivolt. And if we go for large signal tuning with the voltage and current limit, then we will get 11.2 microsecond. It is still almost 6 to 7 times faster with reduced voltage undershoot, because in boost converter it has a property. In buck converter, the time optimal control also reduces the undershoot, but in boost converter, if we increase the duration of on time, the voltage undershoot decreases, because during this time the voltage discharge. So here in time optimal control of a boost converter, you may end up with more current voltage undershoot. So for that you have to put some limit, and that can even achieve faster response. So here also, now since we have learned about constant on time and off time, where what we are going to do, this can be integrated. That means we can use only one DAC, only one ADC, one controller, but some few extra digital blocks, because this is a modulator where we have discussed this modulator value can be updated because in digital, right? Because either we can configure to constant on time or constant off time. So if you configure constant on time, then the value of the on time should be different from the off time. So as a result, you need to just update the timer. So you can see it is only one monoshot timer where we need to update the value of the timer, so that we can configure the same circuit to constant on time or off time. But only requirement, you need to change the sampling age, because it relies on event based sampling, and we will discuss in this. Suppose when you take constant off time control, you see the off time is constant, then we are taking the sample at every here, we are taking the sample here, that means the output voltage is taken sample here. When before switch turns on, we are taking the sample, because it is like an interval 2 sampling, and during the constant on time control, we are taking the sample before switch turns off. That means we are taking the sample right here, close to here. So that means only the changing sampling point. That means for constant off time, we are using the sampling age to be before switch turns on, and for constant on time, we are taking the sampling time before switch turns off. So these ages can be changed, adjusted by this clock. So there is no extra hardware requirement except for those small digital hardware, right? But that controller, everything else, they are common. So we can achieve smooth transition. That means at high load we can go for constant off time, where we can take the best benefit of fast transient, step up transient. During step down, we can take the benefit of constant on time, so we can get a very extremely fast step down transient. And also under light load, once we enter into light load, then we can constant on time, we know about that, it can achieve a very high efficiency in the light load by varying the switching frequency proportionally to the load current, because it is constant on time control, where your switching frequency is linearly proportional to load current in under constant on time control, right, in DCM, and that we have learned in DCM, that we have learned. So this can be very easily programmed using finite state machine, where if it is in continuous conduction mode CCM, then we go for constant off time when there is a step up transient. During step down, we go to constant on time current mode control, and if there is a DCM, we can detect the zero current. Then since the current is 0, so we cannot use a valley current control because it is already 0. So you can use a voltage mesh algorithm, and that is typically used for any. So that means all these blocks are already inbuilt, so you can achieve very fast transient response. You can see there is no additional switching here, because that is the inherent property of the constant off time modulator. And constant on time also you can get very fast transient response, but initially we are using synchronous configuration, so that this can be recovered quickly, and once it comes back, then we go for DCM operation, and there we can enable constant on time. By that way we can achieve very fast transient response and high light load efficiency, and this has been already published. So the benefits and opportunity using variable frequency control: no current loop stability problem, because in either in constant on time control, constant off time control, or hysteresis control, there is no current loop stability problem. So it can be used for wide duty issue operation. And since we are using ripple based architecture, right, so you can use very ripple based control algorithm, because like hysteresis is a ripple based control. So it can be easily implemented in digital domain, and we can easily synthesize or emulate the ripple inside the digital controller also, right. So first controller can be implemented. Structural stability retained, that we have discussed, because in constant on time off time control there is no structural instability. As a result, there is no diffusion saturation, unlike in fixed frequency control. Then the large signal tuning can be implemented in digital, although this can be also implemented in fixed frequency. Then the programmable switching frequency, because since we are using a digital platform, we already have an all digital PLL inherent. So using that feature, we can program the switching frequency and regulate the switching frequency. And then we can easily implement multi-mode control that we have discussed by changing between constant off time on time to take the best benefit as well as high light load efficiency. So we can improve both performance, efficiency, as well as we can adjust the switching period, and we can get very enhanced stability, both fast scale stability, so that subharmonic problem can also be reduced substantially. So with this, I will summarize the stability aspect in digital current mode controls are discussed. We have discussed the effect due to quantization and sampling. Then we have also discussed the deuterium saturation problem and nonlinear behavior in digital control. Then we have also discussed modeling and analysis of digitally controlled converter, and then we also discussed opportunity using variable frequency digital control architecture. In fact, these are just I am touching upon what are the emerging what is going on, some of the architecture, but you can browse through many other digital control architecture. In fact, majority of the commercial product are slowly shifting, not now but maybe in near future, in 5 years or 10 years down the line, you will find that the products are coming in digital, because it offers so many features of flexibility, programmability, tuning, performance, efficiency. So those can be obtained, but we have also observed there are stability aspects are also there, and there are other aspect of ADC DSC optimization, because if there are multiple converter, we may not need multiple ADCs. So you can use the resource in time multiplex mode and you can reduce the requirement. So this is something about the overview of some aspect of digital control and some variable frequency architecture, and I think we will know more about digital control in future lecture, future course. So with this I want to summarize here. Thank you very much.